Recording is rolling. Tuesday, August 16th. You guys remember taking this week to cover a lot of the basics that are going to show up throughout the year. Yesterday did some algebra with you guys. Today going to focus on trigonometry and vectors. Turns out probably going to take more than just today. So I'm thinking all this stuff I had planned for Wednesday might get bumped today itself, but we'll go as far as we can with the trigonometry vectors today. Okay. So this start off actually with a physics type question that that you guys are able to figure out. Remember some math from the past. Okay, then we'll go look back to the math, trigonometry, guys, some other applications there. Okay. So I got this plane. Let's say that I messed up already. Sort of ish. Sure. Thank you. That's again. That plane. I've got a plane flying straight north at, let's say, 100 meters per second. Hey, meters per second, is that kind of like miles per hour, distance per time? Okay, but we're going to be using the metric system. Okay. Now, that's the, okay. Everybody's taking notes, right? You guys taking notes? You guys all got your notes up? Right, so that's the speed of the plane relative to the surrounding air. Now, the plane shot across the ground, probably same story. You point a radar gun of the plane, all reach 100 meters per second. It's all fine and good. But what if this plane is in a crosswind that's blowing east at 100 meters per second? Okay. So, you guys see how I'm drawing arrows, right? These arrows are called vectors. This is the plane relative to the air. This is the air relative to the ground. Do you think it's going to blow the wind off course, maybe like northeast? You guys think? Okay. And notice how I've connected these vectors with called tip to tail. Tip to tail. Right. And if you do that, I only have two vectors here, this one and this one, but you could have like 10 vectors if you connect them all tip to tail. And then if you go from the tail of the first one to the tip of the last one, that gives you what's called the resultant vector. And that tells you, actually tells you two things. It tells you the direction that the plane moves, and also like the magnitude of the velocity, called the speed, relative to the ground. So resultants. Right? Okay. So here's the plane relative to the air relative to the ground, put it all together, and you get the plane relative to the ground. So you watch the plane shadow move across the ground, it's kind of northeast. Okay. Who can tell me what how fast the plane shadow moves across the ground? Anybody figure that out? How fast?
100 miles.
Okay, so it's faster than this, right? Actually, it's the magnitude of this vector, this resultant vector, right? All right. Do you guys remember something called Pythagorean theorem?
Yeah.
Here's one application. So you guys know that on a right triangle, and this is a right triangle, right? Because I have straight north, straight east. Okay. So you can go c squared equals a squared plus b squared, right? If you're solving for c, okay. Now, what was if you take this 100 meters per second and you turn it into a physical square, and you take this 100 meters per second and turn this into a physical square. You take the resultant, whatever that is, we're trying to figure that out, and you turn that into a physical square, which is a pretty big square. Would you guys believe that this square plus this square adds up to this square? Right? That's exactly what the Pythagorean theorem says. Right? So let's pop in some numbers. So I'm trying to solve for C, the hypotenuse. I know A is 100 meters per second. I'm going to square that. Because remember in physics, numbers have units attached to them. Okay. B is also 100 meters per second. We're going to square that. Let's see, what is 100 squared plus 100 squared? It's like 20,000. So C squared is 20,000. That's meters squared per second squared, which is kind of a silly unit, but we're about to square root both sides, right? Or I should have asked you guys. You guys would have said that, right? Square root gives the answer. So C equals, what's the square root? Well, I can do this. Power 0.5 is the square root 141 and change, but basically 141 meters per second. So that is the speed of the plane relative to the ground. If you're down on the ground and you point a radar gun up at that plane, it's going to tell you the plane moving at 141 meters per second relative to the ground. Okay. Right? Because it's going north and also east. Okay. Furthermore, there's one more thing about velocity though, because velocity isn't just speed, it's also direction, which is going to be important. Whenever you're talking about vectors, direction matters. Give you guys some other examples later in class, you guys see why. Okay. But how about this? This angle right here, I'll call this angle theta. Okay. Who can tell me what that angle theta is equal to? Maybe just by eyeballing it, maybe? 45 degrees? Yeah, you guys like 45 degrees? That would be a 45-degree angle, right? So 45, 45, 90 triangle, right? Right, you guys said. Now, what if I didn't make these numbers so nice though? What if it's like 100 meters per second going to the north and like 73 meters per second going straight east, that crosswind, right? Well, now that would be trickier to figure out, right? I wonder if there's some general method that you can always use to find theta, even if it isn't a nice 45 degrees. Right? So let me go review some SOHCAHTOA. We're gonna paddle back and forth between some math stuff and some physics stuff, and because they have cross applications. So let's look at the math side of this. You guys remember SOHCAHTOA? Right? It's an acronym, so it's a mnemonic device to help you remember what sine, cosine, and tangent stand for on the calculator. Your sine, cosine, and tangent keys. Okay. All right. So on a right triangle, and we're going to be looking at a bunch of right triangles today. Side note here, if you ever had any shape, including a triangle that's not a right triangle, like what if I just made some generic triangle? Okay. Like this is just some generic triangle, right? It doesn't have a right angle. Okay. You can always split it into smaller shapes until you get two right triangles. Right? But I have two right triangles. Okay. Point. So really, you can even take a circle and like split it into like a million tiny triangles. Right? Okay. So this could be useful, like regardless of what shape you have. Okay. You can put it in right triangle form. I have a right triangle here. Now I have two acute angles, so I need to specify one of those angles as a reference angle. I'm going to specify this one down here, and I'll call it theta. There's theta. And the longest side of the triangle of a right triangle is called the hypotenuse. Call it HYP for hypotenuse. I'll spell it out. Hypotenuse. Okay. Then relative to this angle I picked, see, I could have picked the one in the top right, but I didn't. I picked this one down here on the bottom left. Okay. The two legs of the triangle. Well, one of the legs is opposite of that angle, and the other leg is adjacent to that angle, adjacent, like next door neighbor. See how the two legs, one of them is not touching it at all. It's not touching the angle theta, but the other one definitely is, like next door neighbor. You see that? Right. Right. So how about all the SOHCAHTOA stuff? Right. So that tells you the definitions of sine, cosine, and tangent. So sine of the angle, which is like a function, right? So sine of the angle is defined as the ratio of what over what. How about opposite over hypotenuse? Right? Opposite over hypotenuse. Right? Cosine of the angle is defined as adjacent over hypotenuse. And tangent of the angle is defined as opposite over adjacent. Okay. You guys remember all that? Right, now that's straight out of the math textbook. In physics, there's a way you usually apply this like 90% of the time. And I'm gonna rearrange this formulas just a little bit to put them in a form that you almost always apply this. Okay. see in physics, you guys know this triangle really refers to maybe something to do with like vectors or vector components. See like this plane, even though it's pointed straight north, it's actually moving northeast because of the crosswind that's also in. Okay, you might want to. Normally, like how it's originally moving, you want to know, well, how much north and how much east is it moving? So it's kind of like backwards of how I gave you guys this problem, right? And if that's the case, then you would know the hypotenuse and you would know the angle, and you would want to figure out what are these two sides, the opposite and adjacent. So if you know this and you know this, you want to figure out what are these two components. That's usually what you do in physics. Okay. I'll give you guys a force example here in a few minutes, but just so you can see it play out. So what if I push this with a force? A force you could quantify in some number of newtons, so pushing force up and to the right. Well, how much up and how much to the right? Right? If I split into components, it would look like this, wouldn't it? How much up and how much to the right? Right? Well, it goes like this. The opposite leg is equal to, I'm going to take hypotenuse and cross multiply it up. Hypotenuse multiplied by sine of the angle. And the adjacent leg is equal to the hypotenuse multiplied by cosine of the angle. Right? I'm going to box those in because those are real important versions of those formulas. And it's the same thing on the left side of the page, just rearranged a little bit. Okay, here's that. Now, how about that third one? Tangent is equal to opposite over adjacent. Right. Now, you could cross multiply adjacent to get adjacent times tangent is equal to opposite, just like we did with the top two equations, and that would be perfectly valid to do. Right. But I want to do something a little bit different with this one. I want to show you guys how to extract theta. Right. Like, what if you're solving for that angle theta? Like, wouldn't that be like undoing the tangent? Like, I know what tangent of theta is. It's this ratio, right? But what if I know what the two sides are, right? The two legs. I want to solve for what angle corresponds to that. Does anybody know how do you extract theta from that? Theta equals. Does anybody know? It's going to go like this. It's not tangent. It's inverse tan. That's the notation for inverse tan. But sometimes that's called arctan. If you're typing stuff into Microsoft Excel, that's the command they use is arctan. So it's like a tan. Arctan of what? Of a ratio. Want to take a wild guess what that ratio is? Opposite over adjacent. That's specifically for inverse tan. You could do a very similar thing with sine and cosine. So theta is also equal to inverse sine of opposite over hypotenuse. Theta is also inverse cosine of adjacent over hypotenuse, right? So you can, more often than not, I'll do inverse tan to get the angle though, so like that. Okay. So put it all together, and here's a good takeaway from different things you do with the sine cosine, the trig functions. If you ever have a trig function of an angle, that will spit you out a ratio. For example, sine of theta is opposite over hypotenuse. Right? That's what all the stuff on the left side says. But if you ever apply an inverse trig to a ratio, that will spit you out an angle. And that's how you can get angle information if you know lots of side information on a triangle. Okay. Guess that? Okay. Now let's go back and check that airplane, because you guys already know the answer to the angle question on the airplane. You just look at my picture and say, well, obviously that must be 45 degrees, right? You guys know it's a 45-degree angle, right, for that. But I want to show that this actually does work. Okay. Let's use this formula right here. Okay. So on the calculator, okay. Oh, how do you access that inverse tan? Well, I see the buttons for sine, cosine, and tangent, but see above them in letters says inverse sine, inverse cosine, inverse tan. Guess that? Okay. So hit the second key on the calculator, hit second in the top left corner, and then tangent. And up on your screen, this should pop up. Inverse tan. You guys see that? Inverse tan? Okay. And I need opposite over adjacent to specify that angle. So wouldn't that be 100 divided by 100? Do you guys see that? Here's opposite, here's adjacent. 100 over 100. Okay. Now, if this works, what number should it say on my screen? 45, and that's degrees, 45 degrees. Yeah, that work. Okay. Yeah, let's real fast check the other ways that I didn't actually write on paper, but we could have done it. Could you do inverse sine of 100 over 141? Because this is 141, right? Remember that? Okay. What's inverse sine of opposite 100 over 141? Hypotenuse. It's also 45. Okay. Now it missed a little bit just because this 141 is rounded a little bit. It's like 141.4 something, but okay, pretty much 45 degrees. You could also do inverse cosine of this 100 over this 141. It's still like, well, there you go. What is it? Well, it's 45 degrees. Did I do a typo up here? No, we're good. We're good. Okay. All right. So you guys got that? All right. Next thing. Let's go with. All right. Let's go with the monkeys and the bananas. Let's try to see some monkeys and some bananas. So I have a bunch of bananas. Those big juicy bananas. And I got some hungry monkeys. Got one monkey up here. And this guy's got a rope tied to these bananas. I don't think those bananas. He's pulling those bananas towards him. Get that? But he's got some competition. There's another hungry monkey. He's pulling straight down on a rope. Now I'm going to turn these into vectors. These are going to be force vectors. Right? Force vectors. I remember what I forgot to tell you guys. Okay, pause real fast. But we're going to do this. Okay. I need to give you guys the definition of a vector and some examples of vectors. But force vectors are vectors, just like velocity vectors are vectors. But what makes a vector a vector? You guys remember this packet from the first day of school? Right. On the second page, with all the variables and units. And on the back of that page, at the very bottom, I listed some definitions for you guys. So there are different kinds of quantities we're going to be working with in this class. There's scalars and there are vectors. Okay, if something is a scalar, that means it only has a magnitude. And I gave you guys a list of examples. Let's say, for example, mass. Right? You guys see this this lab mass right here? This is 1 kilogram. Now, 1 kilogram represents the amount of material. It also represents the amount of inertia. Like if you push on it, the more mass it has, the less it's going to move. If this is floating around in space, is it still 1 kilogram of mass? Yeah. It's still 1 kilogram floating in space. Does it have any weight in space? No, but weight's something different. Weight is a downward force, right? Which puts it in this other category called vector. So vector also has a magnitude, like a number attached to it, but it also has a direction, which is really important. Notice all the arrows that have been drawn today have some direction that matters. Okay, that's what makes them vectors, right? And one example of a vector, here's a bunch of examples. One example is force, and weight is a type of force. Okay? There's Earth's gravity is pulling this straight down. That's the direction, right, of the weight. Right? So just to recap, if this is floating around in space, it has the exact same amount of mass, but no weight. Down here on Earth, has mass again, but it also has a downward force on it, which is a weight. Okay, so mass is a scalar, weight is a type of force, which is a vector, has the direction. Okay. You guys okay with vectors and scalars? Or scalars and vectors? All right. Okay, so back to these monkeys. So we have a different type of vector. It's a force vector. They're pulling with some tension force. Okay, up to the left, down. Okay. Now, do you guys think that those bananas have a net force on them? They're going to accelerate in some direction overall? Right. Which direction do you think those bananas are going to take off? If both these monkeys pull at the same time, like my bananas, pew! Which way do those bananas go? Yeah. Down to the. How many of you think kind of down to the leftish? Kind of down to the leftish. Who thinks that? Yeah, you guys see kind of down to the left? Okay. This guy's really pulling straight down. This guy's pulling mostly to the left, a little bit up. So overall, it's kind of down to the left. You know what? Do you guys think you could do that? I told you guys about tip to tail, didn't I? Tip to tail, did we do that? Yeah, all right. Could I do that? Could I take this bottom one and slide it up, connect it tip to tail with it? tail, tip. And then this would be jump, jump, and the resultant would be kind of down to the left, like I said. Or it could do it the other way. I could take this guy and slide him down this tail to this tip. And then the resultant would be the exact same place. So going from the tail of the first one to the tip of the last one, it's still kind of down to the left. So no matter how you look at it, the bananas overall are going to be pulled down to the left. Won't take off that way. In fact, they're going to accelerate that way, which means they're going to speed up going down to the left. You put a force on something, it's going to accelerate. Okay. Where would you have to put a third monkey to balance out the bananas so that they're in equilibrium and they don't move at all? Where would you put the third monkey?
Oh, right.
Up to the right. Good call. Good call. And draw a third monkey. All right. He's got a tension vector pulling up to the right. Okay. Now do those bananas look pretty well balanced out? I think pretty balanced. Yeah. Okay. So they're probably in equilibrium, right? Okay. Now I've been trying to give you guys lead you guys through an example so far where I haven't even mentioned like sine and cosine yet, but you know that's where this is going, right? You can look at it at a glance, like, okay, I get how those bananas would be balanced out. Right, now we're going to do the component analysis, right? So I need to introduce a Cartesian system so that I have some angles I can measure with respect to, right? And I'm going to introduce, no, there is no such thing as like Cartesian planes in the real world, right? They're just like pulling different ways. So we're going to make up something. I'm going to do something that aligns with the monkey pulling straight down or the sides of the paper, or any version of that, right? So there's my vertical axis, and then perpendicular to that, get a horizontal axis going. Okay. Okay. So now I have a Cartesian system that I can measure with respect to, right? And I need to give you guys some numbers. Let's say that each monkey is equally strong and they're each pulling with 100 newtons of force. 100 newtons that way, 100 newtons that way, 100 newtons that way. Okay. I also need to give you guys some angles. I'm going to tell you guys that this is a 30-degree angle, and this over here is also a 30-degree angle. Okay. You guys good so far? All right. Now, do you guys see how the monkey pulling up to the right and monkey pulling up to the left? The amount that this guy's pulling to the right and the amount this guy's pulling to the left are going to balance each other out. You guys see that? Okay, so we're going to do the analysis that basically confirms that. Okay, and also these two guys up here are pulling a little bit up, a little bit up, a little bit up. And this guy's really just pulling completely down. Do you guys think this up component and this up component is exactly going to balance out with this down component? Well, let's do the math and see if this works out. My picture may not be exactly to scale, okay. But I'm going to take these forces on an angle. I'm going to split them into components. Let's do components. So I can quantify how much to the right and how much up, and how much to the left and how much up. So how much left, how much up, how much right, how much up. Okay. Okay. Guys good? And we're gonna figure that out by using this right here, right? If you know hypotenuse and you know an angle, can you get the two legs of the triangle? That's exactly what we're doing. Okay. Oh, why did I dash them? I dashed these components just to not double represent them. See, if I did solid, that implies that like I'm double counting vectors. Like there's this vector and this vector. No, I'm trying to replace the 100 newtons with the dash vectors. Okay. So what else here? This component. Right. If you follow what we've been doing in your notes, like this right here, this is going to be what times what? How about 100 times sine of 30 degrees? Because it's opposite of the 30 degrees. It's kicked over opposite. So wouldn't this have to be 100 newtons times sine of 30 degrees? Would that be true? Right? You guys follow that? And let's see what that is exactly. What is 100 sine 30? I'm looking at 50 newtons. 50 newtons exactly. Ooh, that came out really nice. 50 on the dot. Oh, how about the monkey pulling up to, well, here, let's get this other component first. Okay. How about pulling strictly to the right? This is the monkey pulling up to the right, kind of up, kind of to the right, but how much? We're going to quantify, right? So this leg of this right triangle is equal to what times what? 100 newtons times, what do you think? Cosine of 30 degrees. Yeah, cosine of 30 degrees. Let's see what that would be. One reason I like this model calculator is because if you have a similar formula, watch this trick. Arrow keys, scroll up, scroll to the right. Replace that sign with cosine. Done. 86.6 newtons. This is 86.6 newtons to the right. Okay. Guess that? Okay. Now, this monkey pulling up to the left. Well, I gave you some, it's the same geometry, it's just to the left, right? Is that so? You do the same equations all over and over again. How much up strictly? I think it's also 50 newtons. Yeah, so I'm gonna label this guy 50 newtons. And how much to the left strictly? What do you guys think? 86.6 newtons. There you go. Okay. Now I'll box in everything vertical and I'll circle stuff that's like right and left, okay, just so we can distinguish what's going on, which axis. Okay. Let me do one more thing, which is define directions like positive and negative directions. Let's call right positive and up positive, which would make left negative and down negative, right? So I'm going to slap in some negative signs. I'm going to call this guy negative because it's to the left, and the monkey is pulling strictly down. Well, also throw in a negative sign there, but 100 newtons down, so that'd be negative 100. Okay. Okay. So then if you go just add up all the forces, okay, now you have to stay within each direction. What's 86 plus negative 86? 0. And what is 50 up plus 50 up, and then plus negative 100? 0. Ah, so are those bananas in equilibrium? Yes, because there's 0 net force. So those bananas are just hanging out there. Okay. Oh, yeah. Oh, yeah. Let's go ahead and sign that on this computer. Right. Okay. Okay. So you guys good with the bananas and monkey? Okay. How about this? If you're going to be an engineer one day, you might be designing some press bridges, possibly. Right. Do you think? Yes. Sure, this kind of works with. Do you guys think that some of these parts of the bridge might be in tension and other parts might be in compression? Do you guys think that every single point on this bridge has to be in equilibrium, just like those monkeys? Because bridge isn't moving. I hope not, right? Bridge is supposed to stay stable. Okay. You guys think that there's an entire college class called statics, where you have to just sit there and just analyze the bridge like this? How about this point? All the forces better sum to 0, just like those bananas. Some may be tension, some compression. Ah, right, guess that. Right. How are we doing here? 14. All right. Right, we sure got everything. All right, do you guys see a page on your desk? Looks like this page. All right, so this has 10 different triangles. Well, there's one picture, but they're all a little bit different. It's got triangle 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, 10 different triangles. Okay. Now, if you know enough information about a triangle, if you know 3 pieces of independent information, that's just enough information where you can figure out everything about the triangle. And this class is really good to be able to work your way around the triangle. So here we go. Okay. So my model triangle here is definitely a right triangle. But you guys remember, I told you guys this before, if you have any shape that's not a right triangle, for example, just a generic triangle, you can always split it down to smaller shapes until you do get right triangles. Therefore, you can always apply this math. Okay. Number 1, I gave you guys an angle, or one of the acute angles, and also the hypotenuse. See on this triangle, we've got side X and Y are the legs, side Z is the hypotenuse. The right angles well, spark to its 90-degree right angle. And then there's angle alpha and angle beta. So there's two acute angles, alpha and beta. Okay. Right. Now, everybody has different numbers, so your numbers are probably not my numbers, unless you're really lucky. So, but you should be able to follow the same processes that I'm following. Okay. You guys have that? Now, if my angle alpha here is 30 degrees, who can tell me what my angle beta is? How much? Yeah. 60 degrees. How do you know it was 60 degrees?
Because there's a right angle, which is 90, so you would subtract 30 and 90 from 180.
Exactly. Yeah, you guys remember that? Is that every single flat triangle, the angles have to add up to 180, right? And if the 90-degree angle, well, let's already pull a 90 out, right? So what did the two acute angles always add up to? The other 90, right? So then, yeah, so 180 minus 90 is 90, minus the 30 that's there leaves you with 60. Okay, right, guys got that? So these two ideally should always add up to 90 degrees. Right. I also gave you guys a hypotenuse. My hypotenuse says 50 meters. Notice that these all have units attached to them, right? Meters could be displacement. So it looks like somebody's walking northeast. Just for example, number 1, somebody's walking northeast. Right? How much north and how much east? Well, it depends how far they went all together, and also what angle they were. Right? Okay. How are you going to solve for x in number 1? How do you solve for x? Are you going to go? You guys are just going to follow these notes, right? Okay. Remember these formulas I had you guys box in? Okay. Those are probably the handiest formulas to use, right? Now, sometimes you might have to go back to some of this other stuff. Okay. I bet if you follow these box in formulas, that'll carry you a long way on this page, right? Pretty handy box in formulas right there. So I'm going to go x is equal to z times, well, I got a couple of options for x. Say I'm playing off this angle alpha. If I'm playing off alpha and I want x, which is adjacent to alpha, is that sine or cosine? Adjacent to alpha, that cosine of alpha, right? Hypotenuse times cosine of alpha, flip side, we get you the adjacent leg to that specified angle, right? Let's try that. Oh, plug in some numbers. So I have 50 meters displacement, multiply by cosine of 30 degrees. What is 50 cosine 30? That is 43.3 meters. That's 43.3 meters. Okay. Is that right? I didn't have to do it that way. I could have done it a different way. What's the other way you could have done this? X is equal to what? G times. If you're not doing cosine of alpha, you could have done what compared to beta? Is side x opposite of beta? Which means you're going to apply what trig function? How about sine? Good call. Right? Right? Let's plug in some numbers. So I got my 50 meters for z, that didn't change, times sine of 60 degrees. Okay, so cosine 30 degrees, sine of 60 degrees, they should refer to the same side. We're going to find out. 50 sine 60 degrees. Oh, it's still 43.3 meters. All right, it's the same thing either way. That method, that method. They were the same thing, right? Okay. How about side y? I can think of 3 ways to solve for side y. What's one way to solve for side y? Could I just do this sine cosine stuff, but just flip alpha and beta? Okay. Yeah, okay. So side y is opposite now of alpha and adjacent to beta, which is the opposite of what we did for x. Okay. So I could do that. Let's try that. You can do y equals z times sine of alpha, or skip some lines here. Y equals z times cosine of beta. Either one of those should do it for me. Okay. So take 50 meters times sine of 30 degrees or 50 meters times cosine of 60 degrees. Should tell me the same thing. Let's see if that's true. 50 sine 30 degrees is 25 meters. Or if I do it this other way, 50 cosine 60 degrees is also 25 meters. It's the same thing. So 25 meters. Okay. I said I was thinking of 3 ways to do it though. So what's the third way you could have gotten y? Using the
If it's a 30, 60, 90 triangle, I think it would be half or
yeah, that's a good trick too. Yeah, you guys notice that? Which is whenever you have a 30, 60, 90 triangle, see how the short leg compared to the hypotenuse is always a 1-to-2 ratio. So it's always half. Yeah, that's a pretty good tidbit to know, right? Yeah, I bet you guys are gonna see that a lot. Right? Hey, could you have done Pythagorean theorem? Let's try it out. So x squared plus y squared equals z squared. Okay. Now, notice if you do Pythagorean theorem, that has nothing to do with the angles other than you have to have a right triangle. Okay. But it's everything to do with the sides. Could you solve for y knowing everything else? Okay. At this point, well, I know x was like 43.3 meters. Square that. I'm solving for y, span squared, and then z was like 50 meters. Square that. Okay. So 43.3 squared, like 1875 plus y squared is 2500. Okay. Okay. 2 steps left. I think I can squeeze them in the bottom of this page here. I'm going to subtract this over. So it's 2500 minus 1875. That's 625. So y squared is 625, not square meters. And last step is to do what to both sides? Take the square root. Okay. So what's the square root of 625? That is exactly 25, and then meter squared is just plain meters. But that's exactly what we got before using the sine and cosine method. Look at that. It's the same thing, no matter how you do it. Okay, so there you go. 3 perspectives. They all lead to the same thing. 25 meters. Okay, you guys good there? Questions so far? All right. So example number 1 was really in line with these notes, especially. And some of these other ones, well, they're like puzzles, right? You guys see this like a whole page of puzzles. Okay, let's do a harder one. How about number 7? Number 7, good. Okay, so number 7, I gave you the 2 legs, and also, of course, the fact that it's right triangle. So let's start with hypotenuse. How can you solve for the hypotenuse on number 7? What's a good method? You guys thinking Pythagorean theorem? Yeah, Pythagorean theorem, number 7. Say Pythagorean theorem. So z squared is x squared plus y squared. Okay. And I know x and y, I gave this to you. So z, we're solving for squared. What's it, 4 and 3? So 4 meters, 3 meters. Right. So z squared is 16 square meters plus 9 square meters, which is like 25, right? So 25 square meters. And your very last step is to do what besides? Take the square root. Square this coloring. Square root. 5 meters. 5 meters exactly. Huh. 5 meters exactly. Oh, well, of course it should have been 5 meters exactly. You guys would have known that before you ever started school this year, because that is a what triangle? How about a 3, 4, 5? You guys see it's a 3, 4, 5 right triangle? Yeah. Uh, and I did give everybody unique numbers on their page, but your numbers might say 6, 8. Here, if your two legs are 6 and 8, what does Z have to be? 10, because that's also a 3, 4, 5 proportion, isn't it? Yeah. Or maybe yours says like a 60, 80, and this would have to be 100, right? It's all 3, 4, 5 proportion. Okay. All right, now we got to figure out what are the two acute angles. How do you solve for either one of those? Ah, you guys are on. Look at that. Look at that. Yeah, like an inverse trig. For example, inverse. Now, if you do inverse tan, it's specifically the ratio of the legs. So yeah, let's do that. Let's try inverse tan. So I could say this angle alpha, or actually, let me go back a step. I'll say tangent of alpha is equal to y over x. Therefore, alpha is equal to inverse tan of y over x. Right? It's like undoing the tangent function. Right. All right, let's pop in some numbers. Alpha is inverse tan y over x. That's 3 over 4. Oh, and those are newtons. So newtons, but that doesn't matter anyway because cancels out. Wait, did I? Oh, I did silly. But, no, this is just a little mistake. But in my last example, I put meters all over the place. It should have been newtons. Oops, it should have been newtons. All right, that's okay. It comes out to newtons. All right, the numbers are still good though. Right, so inverse tan of 3 over 4 is that rounds to 37 degrees. I'll call that 37 degrees. 37 degrees. I have to go here, alpha 37 degrees. Okay. Does that look about right? Like if y is a little bit less than x, 3 compared to 4, it should be a less than 45 degree angle. Oh, that is a little bit less than 45 degrees. I can believe that. That looks about right. Okay. All right. You could have done something a little different. You could have done inverse sine of y over z or inverse cosine of x over z. Let me show you guys that those also work. Inverse sine, so second sine, inverse sine of 3 over 5 is also 37 degrees. Inverse cosine of 4 over 5 is also 37 degrees. There you go. There's 3 different ways to get that number. All right, now that we have everything about this triangle except for beta, I can think of several different ways to get beta. What's one way to get beta? Could I do an inverse tan but just swap the definition of what's opposite and what's adjacent? I could probably do that, right? Could I do tan beta must be x over y. Therefore, beta is equal to inverse tan of x over y. Let's try it that way. Beta equals inverse tan of 4 over 3. That's newtons. What is inverse tan 4 on 3? 53 degrees. 53 degrees rounds to 53. Now, how many guys were thinking, oh, I could have done that even faster because I know that alpha and beta have to add up to what again? 90. So you could have just done 90 minus 37. I bet a lot of you guys did that anyway, right? But yeah, in fact, they do add up to 90 degrees, don't they? Yeah, they sure do. Right. Guys, good day. All right, so flip this page over, at least get you started on the side, and then we're going to have to do some more in class tomorrow. But do you guys see 5 different triangles and then 5 different rows on this table? Right. So each row applies to one of the triangles. And what's in all the columns? Well, some of these columns say measure, and some of these columns say calculate. Right? Do you guys see how there's some dark rectangles around some of these columns, right? The idea is that if you make a direct observation, a direct measurement with your science tools, like your ruler and your protractor, okay, and then you pick up the calculator and start doing some calculations, that you should be able to get the same number referring to either of the sides of each triangle, regardless of whether you calculate it or measure it. Right? So this is where the science and math all comes together. So let me pick Maxwell and pick guys through Maxwell. Alpha, I need to measure angle alpha for Maxwell. So I'm going to take the protractor, this note's direct measurement, park this node right on this corner, zero out this leg right there. And then the hypotenuse sweeps through 22 degrees. So alpha is 22 degrees. Now I could have, here's maybe an easier way to measure it, possibly. Measure counterclockwise, or sorry, clockwise instead of counterclockwise. Flip the whole thing upside down, park the node of the protractor right on that corner, zero out the hypotenuse. And the short side, well, this like crosses through also 22 degrees. These triangles might be a little bit on the small side. So what you can do is extend each leg like that. And if it didn't work before, it should definitely work now. 22 degrees. It actually goes through 22 or 158, right? Depending on which side of the protractor you're reading through. So do you guys know that alpha and beta for all these triangles, they're all acute angles, right? Which means they're all less than 90 degrees, which means I'm not going to pick 158. I'm going to pick 22. Right? You guys get that? Okay. Well, Bill's about to ring here in a few seconds, so this is going to have to be our pause point. Yeah. I'm leaning toward, I think tomorrow I'm going to get you guys time in class to help each other out doing these. And then we'll take all that science and measurement stuff and dimensional analysis and probably push that off to Thursday and thinking. That's the plan right now anyway. All right, who's got any questions? Oh, yeah.
You know, like you know, have I'll second this one.
Yeah.
Okay.
Also, you can do PowerPoint time.
PowerPoint.
Yeah. All right. You guys have a great day.
Have a great day.
Oh.